Hello and welcome to our lesson on arc length and speed, and hopefully you'll see the connection between those by the end of this. But what we're going to start with today is a connection to our previous topic where we talked about measuring angles in radians. So I have our unit circle here. This would be our circle with a radius of 1 unit. Then I have a couple of extras, but hopefully we can see that we have an angle that's in standard position in each of these 3 circles that I have graphed. And also I'm hoping that you know the measure of that angle. So the measure of that angle, right in between our 0 degrees and our 90 degrees, has to be 45 degrees. And if you're thinking in degrees still, that's totally fine. So we have a 45-degree angle in here. But remember, let's go back to our unit circle for a second. Our unit circle that has a radius of 1, right? Radius of 1 means that its circumference, which is 2 times pi times radius, would have to be 2 pi. And so if we were 2 pi all the way around the circle, let me change to my highlighter. If all the way around the circle was 2 pi, then we said halfway point there, 180 degrees, would be 1 pi, and that 45 degrees would be 1/4 of that 1 pi. So not only could we call that a 45-degree angle, but we could say that is equal to pi over 4 radians. Okay, so that's a pi over 4 radian or 45-degree angle there. But the radian measure, remember, is specifically and directly related to the intercepted arc. So when I'm talking about that pi over 4 radian measure, what I'm focusing on is the length of the arc that's intercepted here. So the length of that arc, we could say, is pi over 4 radians. Now what happens if we extend this out? So instead of looking at the unit circle, let's say we go out to a circle that has a radius of 2 units. So that's the blue one that I have graphed there. Now what's happening at this intercepted arc, or what is the length? What's happening to the length of that intercepted arc? So let's talk about the circumference for a second. Remember, circumference is 2 times pi times radius. If my radius is now 2, then my circumference is now 2 pi. So not only have I doubled my radius, I have doubled my circumference. Which means, think about the full circle here. If all the way around this circle is 4 pi, then from here to here would be 2 pi. And this is 1/4 still, but it's of the 2 pi. Right, so the 1/4 now of the 2 pi means that that arc length is doubled as well. So this arc length is now 2/4 pi. Okay, it's 1/4 of the 2 pi, right? 1/4 of the 2 pi, which would be 2/4. Doubling our circumference, or doubling our radius, doubles our circumference, which also doubles our arc length. Okay, so then what if we went to a radius of 3? We can see the arc length here. Again, it's bigger. The question is, how much bigger? Well, again, our circumference being 2 times pi times a radius of 3 now means it's 6 pi. So what's happened from the original? From 1 to 3 is I've tripled, and from 2 to 6 is I've tripled. So what's going to happen to the length of the arc there? It's going to triple as well. Now it's going to triple from where we start. So we're going to always use that unit circle radian measure as our reference. If we get bigger, how much bigger? If we get smaller, how much smaller? From that reference point. So if we took pi over 4 and multiplied it by 3, the length of this arc, to be consistent here, would be 3 times the pi over 4, so 3 pi over 4. Okay, so this is going to offer us actually a general formula that we can use to find that length of that intercepted arc, which we'll call arc length. If we know our angle measurement, we'll call that theta in radians. So originally, what is that radian measure when we're talking about our unit circle? If we multiply that measure by our radius length, we will end up with the length of our intercepted arc. Okay, so that's what we're going to generalize here at the start of our notes. An increase in circumference is directly proportional to an increase in the radius length. So what I mean is if the circumference doubles, the radius doubles, or vice versa, right? If the radius doubles, the circumference doubles. Or if the radius was cut in half, the circumference would be cut in half. So those are directly proportional, directly connected. And likewise, that will be true for radius length and arc length. So the arc length, remember that's just another word for that intercepted arc. So those changes are directly proportional. If one doubles, so does the other. And so if we have a generalized picture, let's go ahead and put an angle in standard position into this picture. So here's our angle. If we know our angle, again, in radians, what is that original radian measure, the ones we talked about on the unit circle, or the ones that we could convert our degrees to by multiplying by pi over 180? What is that radian measure? If we multiply it by whatever the radius length is, it's going to tell us the length of this intercepted arc. And we're going to give that a variable as well. We're going to call it s. So arc length, we use the letter s for. Not the best of variables, but it's just what we got, okay? So we can use the formula that says that that arc length, again, is going to be equal to our angle multiplied by our radius. That's exactly what we saw happening over here. We take our angle, pi over 4, multiply it by our radius of 1, we still get pi over 4. Multiply by a radius of 2, it's doubled. Multiply pi over 4 by 3, and it's tripled. So whatever that angle is, which again it has to be in radians, if we multiply by the radius length, we get the arc length s. Now, just kind of by default, we could rearrange this equation, so also keep in mind, like, if I knew the arc length and the radius, I could work backward and find the angle. Like if I wanted to solve for theta here, I could divide r over. So I could also say from this formula that theta, and wow, I don't know what just happened with my pen there, that theta would be equal to our arc length divided by r. Or if I wanted to solve for r, I could say that r, this would have to be divided over, would be our arc length divided by our theta. And again, this is all, sorry, that's the edge of the iPad, it looks a little bad, all predicated on that theta measurement being in radians. Okay, so we should be able to find any arc length given any radius if we know the angle. And just one more term here to throw in. When we have an angle that's centered in the circle, like most of our, like all of our angles in standard position, we technically call that a central angle. That's where the vertex is at the center of a circle. And then I don't know that it's super important that you have it, but I might mention it and I don't want you to freak out. Like, what is this new term? So a central angle just means the vertex is at the center of the circle. Alright, so let's practice using our formula. So to find the length of the highlighted arc. So I'm trying to figure out what this arc length is here. We can call it S. I know from my formula, S is going to be a product of my angle, that's in radians, and my radius. So in this case, I'm going to take my angle, clearly in radians, it's got that pi in it, so 2 pi over 3, multiply by my radius length, which is 17 yards. And so S is going to be, technically 17 times 2 would be 34, so 34 pi over 3 yards. Now that's kind of hard to conceptualize, so I would probably want to approximate this as well. I forgot to bring my calculator in, sorry. So 34 pi divided by, and I forgot the 4. Pi divided by 3 is approximately 35.6-ish. 35.6-ish yards. Did I read that right? Okay, sometimes I flick away the calculator and I'm like, yeah, did I lose what I got? Okay, so let's look at number 2. We're doing the same thing, trying to find the length of the intercepted arc there, but notice our angle is given to us in degrees. And that degree measurement's not telling us anything about that arc length. We need to convert it to radians. So I can do this a couple ways. I can make the conversion for my angle and then plug that into the formula, or I can just put it all in the formula. So again, my formula... What is going on here? My technology. My formula is to find the arc length, says take the angle, multiply by the radius. So my angle is 60 degrees, but that 60 degrees has to be multiplied by pi over 180 to convert it to radians. And then I got to take that and multiply by my radius, which is 16 miles. That's ridiculous. That's a long radius is a big circle. Okay, so I can set it all up like this, or if that's confusing, let me just show you another path. I could take my 60 degrees on the side here and convert it and say, okay, that's going to be pi over 180 when I multiply, so that those degrees are going to cancel. And I could see that 60 over 180 is going to reduce. The zeros would cancel, and 6 goes in 18 three times, so that's going to be pi over 3. So if I wanted, I could just say this is going to be pi over 3 radians for my angle multiplied by 16 miles. So you got either option. We're going to do this often, and I don't want to have to necessarily make a conversion on the side and then plug it into my formula. So I'm going to probably tend toward just making the conversion in the formula. Just again, remember that angle has to be in radians. Okay, so I'm going to get rid of this. And here we had degrees and we had degrees. We got those degrees to cancel. Okay, so our arc length, if we were to get an exact answer, again, I could do some reducing. So this is technically 60 over 1. And so we're looking at, and this is 16 over 1. And let me go to my calculator so I don't mess it up. So on the top of my fraction, I have 60 and 16. And then on the bottom of the fraction, I have a 180. And the calculator will nicely do all that multiplying and dividing, reducing for me. So the 60 times the 16 on the top and then divided by the 1 and the 80 on the bottom is going to reduce to 16 thirds. I just can't forget about pi. Okay, so technically on the top is going to be 16. Let me go back to red. Sorry, 16 pi, and on the bottom is going to be 3. And again, this is miles. That's my exact answer. And now to approximate that, I can just stick the pi in here. And then we're looking at about 16.8-ish. And these were, again, miles. Okay, so either answer, I think the exact answer is kind of preferred. Approximating decimal is not always ideal, but when you're working on your assignments in Canvas, it's going to ask you to put her in a decimal because it doesn't understand pi. It's a little limited, our technology, sometimes. Okay, so pretty straightforward. I'm going to also assign you a couple of word problems similar to these. Not too terrible. If you remember, the formula we're using is pretty basic. So if we look at number 3, a rope is being wound around a drum with a radius of 0.8725 feet. How much rope will be wound around the drum if the drum is rotated through an angle of 39.72 degrees? So we know the angle of rotation, and we know the radius there. So we have an angle, we have the radius. What they want to know is how much rope is going to end up coming along the circle, how it's going to wind there after that degree of rotation. So actually just this little degree of rotation. So how much rope is that for that rotation? Again, that's arc length. So our arc length is our angle multiplied by our radius. The angle, though, is 39.72 degrees. Gosh, I don't know what my pen is doing. I am so sorry. 39.72 degrees. But I want that to be radians. I'm going to multiply by pi over 180 to make those degrees cancel. And then there's my angle. So it's like 2 steps to get my angle there. And then I got really sloppy on this. I'm so sorry. Just going to have to deal with me, right? Alright, then my radius. Radius is 0.8725, and that's feet. So now, I don't think we're going to be able to really get an exact answer out of this. So let me just put this in the calculator, see what it says. 39.72 multiplied by pi divided by 180. And then, get out of the fraction, multiplied by 0.8725. And we get an approximate length of 0.605-ish. I don't know. See, I'm like rounding all over the place. Tens place, hundreds place, whatever. It doesn't really matter unless you're asked to specify. Maybe I'll go 0.61 feet on this one. And it doesn't specify word around, so like I said, if you're not told, I guess the more you keep, the better, the more accurate it is. It's just not one of those things I concern myself with unless it tells me. Alright, so there it is. That's the length. Not terrible. Here's another. It says 2 gears are adjusted so that the smaller gear drives the larger one. So you get a visual of what happens here. As you move one gear, it's moving the other one. If the smaller gear rotates through an angle of 225 degrees, through how many degrees will the larger gear rotate? So we're going to rotate this angle, let's just say some amount of degree. Let's start it right here, okay? Well, actually it says we're going to rotate 225 degrees, and that's really tiny in there, so I'm going to say theta in there. That's Q. Theta in there is 225 degrees. It tells me that. So I'm going to rotate this 225 degrees. How much distance am I covering along this arc if I rotate 225 degrees is something I can find, and that's what I'm going to want to find, because that same distance of rotation here is going to be the distance of rotation here. Okay, so whatever that length is here, let's call it S, it's going to be the same length happening there. So let me find it on this side first. Again, it's going to be angle times radius. Angle, they told us, is 225 degrees, but that needs to be converted. So multiply by pi over 180. Unless you already know the conversion, 225 degrees, that's just 45 degrees into quadrant 3, which, remember, those 45s are fourths, so not 4/4, but another fourth would be 5/4. Anyway, side note. And then we're multiplying by a radius, and I wrote through it, so I cannot read it. 2.5, undo. So put too many undos. 2.5 here. So that means the arc length that I'm looking at is, drumroll calculator, 225 pi over 180. And my fat fingers, I don't know if you have this problem. Mess these things up sometimes. What in the world? Okay, and then multiplying by 2.5. Okay, so we have, for our arc length here, let me make this an approximation. I'm going to call this about 9.817. I'm going to keep a little more of the decimal here, although I don't think I am going to have to round for the next part. So now I know that this gear is going to be covering the same distance because they're linked. Whatever distance the one turns, so does the other. The question is, what angle of rotation is created there? So this time we're looking for theta. So using the same formula, theta is going to be equal to our angle multiplied by our radius. So I know the value of the arc length this time is 9.817-ish. My pen. Silly pen. Now that was a silly me, not the pen. So 9.817, I'm going to plug in for... What is this thing doing? You see it's making these crazy lines? Okay, I'm so sorry. So angle, we're looking for. Radius we know, so I can plug that one in as well. So it's really not too bad if I want to... oh, I shouldn't put that there. Solve for my angle. If it's being multiplied by the radius, all I have to do is divide that over. And we kind of said that in the very beginning, the other version of the formula, right? That radius, or that angle measurement, would be that arc length divided by the radius. So we're going to say theta is going to be 9.817 divided by 4. I don't know why my pen is freaking out. 4.8. Now, I rounded here, and then I'm going to have to round again. So to avoid double rounding, notice I already have that exact answer stored into my calculator. So what I'm going to do is take that exact form, not my rounded one, take that whole amount and divide it by 4.8 so that I don't have to round twice. So now I can see my angle is going to be about 2.045-ish, whatever. But this is radians. Okay, remember when we use the angle in the formula, we're looking at a radian measure. So we have one more step to finish this problem off because it asks us how many degrees. So now I got to take this and convert it to degrees. So to convert to degrees, we have 2.045 radians. Remember, to go to degrees, I want the degrees back in the picture. That means 180 is on top of that fraction, and I got to divide by pi. So what's this going to get us? Again, I don't want to round, so I'm going to keep in my calculator problem here, keep working with what I've got. So there's my exact decimal still in my calculator. Now I want to multiply it by this fraction of 180 over pi. And now I can see I'm at 117.19 degrees. And that's going to be our final answer on that one. Okay, so not hard work, but definitely some places you got to be careful so that we're not, rounding. The more times you round within one problem, the more inaccurate or less accurate your work is going to be. So just be careful with those rounding. See, now I box one thing in, and I got to go box in the rest. I don't know if you're laughing at me, but I'm so sorry. Okay, between my technology issues and my OCD issues, you're just probably tired of this. Alright, so there's one concept that is going to relate to the next concept. So instead of just calculating these arc lengths, what we're going to look at when we flip the page here is speed if we have an object moving along that arc length. So if an object moves along an arc, so like in this picture we have a, let's say this point P is moving along this arc, and right now it's there. Okay, there are technically two speeds that we can measure from this picture. Not only is the point moving along the arc, but also the angle is changing. So the arc length here is going to be changing as that point moves. If I go farther, it gets bigger. The angle is going to change. As I get farther, it gets bigger. So those two different changes are different speeds that we can measure. The first one we're going to call linear speed. When I say linear speed, it's the speed that we know, okay? When we talk about speed, like let's say you're traveling on the freeway going 60 miles per hour, that's your change in position in your car as you're moving around along the freeway. It's the same for an object that moves along an arc, or this point P that's moving along the circle. So that's speed as we know it. We're just going to call it v for velocity, or linear speed. Okay, so linear speed is going to be denoted by the variable v. And the linear speed, again, is speed as we know it. It's how fast the position of the object is changing over time. So how is your position changing over time? Okay. The other thing that's changing is the angle. So not just your position or your distance changing over time, but the angle changing over time. Now that angle changing over time is, or how that angle changes over the time is what we're going to call angular speed. And angular speed gets another variable. It's that one that looks like a W. That's technically called omega. That measures how fast that corresponding angle is in radians, again in radians, is changing over time. Okay, so these two speeds, again, angular speed and linear speed, we've got some formulas for, like why so many versions of the formula. So angular first, again, angular speed we're going to call omega. It is how the angle is changing with respect to time. So all we're going to do is take the angle and divide it by time, right? That should make sense. How is the angle changing over time? So take the angle, again, in radians and divide it by time. So it's very important when we're dealing with arc length, and it was what's happening here, and all these distances, that is a radian measure. It's got to be in radians. Okay? Now, linear speed, or you can think about it as a velocity v, is, again, that's the one we know. So you've probably seen the formula for distance equals rate times time. So if I said I was going 60 miles per hour on the freeway for 2 hours, I would multiply those, and that would show me that I've gone a distance of 120 miles, right? It's the same formula here. If I wanted to solve for the rate, which is another word for speed, I would divide the t over. So I would say my rate is my distance divided by time. That's the same thing we have here. So we're going to call the rate or the speed, or in this case the linear speed, v. And then the distance that we're traveling, because it's on the arc of a circle, we're going to call that s. That's the arc length. That's the distance traveled in these situations. And then time is still time, so still t. Okay? So hopefully that makes sense. But why do we have so many other versions? because there are connections between these things. So on the front of the notes, we said that the arc length can be found by multiplying the radius and the angle. So instead of just taking s and dividing by t, we can also do r times theta and divide it by t. And then because here we defined theta over t as w, then theta over t could be replaced by w. So instead of r times theta over t, r times w. Not w, omega. But you're going to read it as w. That's why I keep saying that. Right? Okay. So we have pen issues. Okay. So that's going to be in radians. So we have all these versions. Hopefully, you'll have the information to be able to use one of them. Let's just look at an example so you can get the baseline of using some of those formulas. All right, so number 5. It says, suppose that the point P is on a circle with a radius of 10 centimeters and ray OP is rotating with an angular speed of pi over 18 radians per second, where O, I'm assuming, is going to be the center of our circle. So if we were to sketch this out, nice little cheat tool I have. Sometimes it works with me. Okay, so what I have is an angle being generated by P. So I'm going to draw this out. Okay, so here is the center of my circle O, and let's call this point P here. So point P is on the circle with a radius of 10, so let me put that in. And it's rotating. OP, that's the terminal side of that angle, is rotating with an angular speed of pi over 18 radians per second. So that means omega, our angular speed, is given to us. Pi over 18 radians per second. And again, the radius was given to us as 10. And then if we look at part A, it gives us another thing here. It says to find the angle generated by P in 6 seconds. So we also know that the time is going to be 6 seconds. Now let me go back to the question for part A. It says find the angle. So what's theta? Theta, what is theta? We know that one. We've seen a couple versions of this, but let me go to what we're talking about here, because we're talking about this point P moving or rotating, so we're dealing with speeds here. I'm going to get it from this version of the formula here, just like I can manipulate distance and rate and time. Let me erase this. So that formula says that omega is equal to theta divided by t, by time, which means if I multiplied both sides by t, I could say that theta is equal to w omega times t. So I'm going to find my angle by multiplying the angular speed that was given to me, so pi over 18 radians per second, and then I'm going to multiply that by time. And what's my time again? 6 seconds. Sorry, it's right there in front of me. And so if I reduce the 6 and the 18 to 1 and 3, this becomes pi over 3, and that's going to be radians. And why are the units radians? I mean, obviously we're finding an angle, and I should have been more clear when I wrote this, but this is radians per second here, and then we're multiplying by seconds here, and that's over 1, so we see that those seconds reduce out and leave us with the radians, so hopefully the units matching up to radians makes sense. So pi over 3 radians, that's the angle that's created there in 6 seconds. That would be the angle of rotation in radians. Now, part B is asking us to find the distance that's traveled by point P in that same 6 seconds. So the distance traveled by point P, that is the arc length that we're looking for here. So we know arc length is equal to our angle multiplied by our radius, and that's all information that we have. So we know our angle, we just found that that was going to be pi over 3 radians. And we know that our radius length is given to us as 10 centimeters. And so we just multiply by 10, which is, remember, 10 over 1. We get 10 pi over 3 centimeters. And I should put my units in there, but centimeters. Okay, so now I know The angle that's generated, I know the distance that it's traveled, which was the arc length. The last component is to, excuse me, find the, the linear speed, the velocity. Okay, linear speed v, which we said is that arc length divided by time, the distance divided by time, right? Distance is just an arc length. When we found that distance, we said it's 10 pi over 3. I just need to divide that by the time, which was 6 seconds. And if you're not so good with fractions, you can by all means put that in the calculator. But remember, this is 10 pi over 3 being multiplied by the reciprocal of 6, which would be 1/6. And so we get 10 pi over 18, but that reduces to 5 pi over 9. And what are the units? So this was centimeters per second. And it says in the problem, but again, it should make sense based on what we have in our setup. So 5 pi over 9 centimeters per second. Now I left all of these answers in exact form because that's preferred. Just mental note, when you go to Canvas, it's going to ask for decimals because it's just an easier way for me to create those problems. So each of those you should be able to put into a calculator and approximate. Okay? Alright, one last problem, and then you can be done with me. Last one says an industrial circle saw blade has a 10-inch radius and spins at 1000 RPM. Find the angular speed of a tooth of the blade in radians per minute and the linear speed of the tooth in inches per minute. So based on some very limited information, we're trying to find angular speed and linear speed. So first bit of information is that we're looking at a circle that has a radius of 10 inches. The second thing it says is that this thing spins. That means it rotates at 1000 RPM. What does RPM mean? It means it's making 1000 revolutions per minute. That's what RPM stands for. So that's how many full circles it's going to make in 1 minute. Okay? So let's find the angular speed first. I think that's going to be easier on this one. When I go to find the angular speed, technically I'm looking for the angle divided by the time. So the question here is, what is the angle? When it's making the 1000 RPM, the 1000 revolutions per minute, so it's going a full circle, which remember in radians is 2 pi. It's doing that 1000 times every minute. So we're making an angle of 2 pi radians 1000 times in 1 minute. That's our time. So our angle is 2 pi, but again, it does it 1000 times in that time of 1 minute. So 2000 pi radians per minute is our exact angular speed. Okay? And again, you could approximate that with a calculator if you needed to. Now we can make calculate our linear speed. So for linear speed, remember lots of formulas. The easiest one to use would be this one, because we know the radius length and we just calculated the angular speed. So one version of our linear speed formula says to take r and multiply by angular speed. So we're going to take our radius that they gave us of 10, and we're going to multiply by our angular speed, which we just found was 2000 pi. And so when we multiply by 10, we're basically just going to add a 0, which means this is going to be 20,000 pi, and this is inches per minute. Alright, and again, both of those are things you should be able to approximate with the calculator. I guess I could take a second to do that here. So let's say this one's going to be approximately, calculator. Sorry if I'm freezing, my pen's not working. Luckily I can use my finger for the calculator. Okay, so 2000 pi, 6,283.19-ish. Pen, yay pen. Okay, 6,283.19-ish. And then the next one my goodness, if I just add a 0 in here, just basically moves the decimal. So 62,831.85. It's really the 9 here, but unrounded. So I can go to the hundredths place again. Okay, so there it is. Again, not so bad using formulas, just understanding which version of the formula is going to work best for the information that you're given. Hopefully you're good to go for your assignments. But as always, if you need any extra help, just reach out. Till next time, take care.